We are now going live.
Okay.
We're preparing to stream. Okay, we are now live on YouTube. Set this up. There we go.
Okay, hello everyone, and welcome to the first ever Manchester Futurist event live on YouTube. I'm Georgia, and I'm your host for this evening. And we're really excited to be trying this new platform, bringing live presentations back to you. And today we're very lucky to have our first presenter be Dr. Aravind Vijayaraghavan, joining us from Manchester University. Aravind is a reader in nanomaterials, and he's here today to talk to us about the future of graphene. So we're hoping that this evening is similar to our format pre-COVID, and is a bit more similar than the podcast we'll be doing. Aravind's going to give us a talk, and then at the end we'll be accepting questions from you. So please write them in the chat, or you can either tweet us at Manchester Futurists, which is at MCR Futurists on Twitter, and we'll pick up your questions and we'll be able to answer them. So as always, we have some rules in our code of conduct, which you can see here. The main rule is basically be nice to each other and to us and to our lovely presenter, and give our moderators some slack in the comment section, like give them an easy job. And you can get in touch with us on social media. We are on Twitter and Facebook. Please follow us there for our updates on our next event. We've even have LinkedIn now. And we've left Meetup, and we're focusing our efforts on these platforms, social media. So Twitter and Facebook are going to be where you find out about what's happening next with us and all the different things that we're up to. You can also catch up with our videos on YouTube on this channel. And now we realise we've got a random link at the moment, but when we get to 500 subscribers, which I'm sure won't take long, judging on the quality of the amazing presenters that we have, we can change it to our name. And so that's a really good reason to hit the subscribe button and stay informed of everything that we're up to on YouTube. So yeah, over to Aravind.
Hello, hi. Well, thank you for this invitation. I think it's going to be a fun evening, right? Let's see if we can get this technology to work. I'm going to try my screen sharing. All right, I need to make sure to click all the correct options. Okay, can you see my slides? Cool. So I will tell you today, I'll talk to you today about graphene and what I call materials in flatland, and I'll explain what that means. As an introduction, I'm a reader in nanomaterials in the Department of Materials at the University of Manchester, and I basically do research in graphene and other nanomaterials and related two-dimensional materials. So I'll tell you what that means in a minute. So this is about my research, not just my research, but what we're doing at the University of Manchester and actually all around the world on these two-dimensional materials and what's the potential and the future of these materials. So I'll start off by telling everybody a bit about what is graphene, a very simple introduction. Graphene is essentially graphite, which most of you are probably familiar with. It's what you find in pencil lead. It's made of carbon, and in graphite, the layers of carbon are arranged in flat sheets. Each sheet is made of one layer of carbon atoms, and one of these layers is graphene. So it's one single layer of carbon atoms. You can see here in this schematic, each dot is a carbon atom, and you've got a sheet, and that's graphene. Okay, it's one layer of atoms. So basically, it's the thinnest material you can ever make because it's just a single layer of atoms. Now, there are materials that are related to graphene. Like, for example, if you roll this sheet of graphene up, you get what's known as a carbon nanotube. If you stack many of these sheets of graphene together, you'll get graphite. And if you cut the graphene into this very specific shape that you see here and you roll it up, you can get a ball. And that's known as a fullerene, which has basically exactly the same shape as your traditional football. So it's got these patches of pentagons and hexagons. So you can see from this cartoon that if you have a sphere, a small sphere, that you can think of that as a dot. So that's called a zero-dimensional material. If you have a tube, that's a one-dimensional material. If you have graphene, which is a sheet, that's a two-dimensional material. And if you stack all these graphene sheets on top of each other, then you get graphite, and that's a three-dimensional material. So we'll focus today on understanding what is a two-dimensional material and what's the future of that. Okay. So a brief history of where we get graphene from. The concept of graphene itself is about 70 to 80 years old. It was first sort of theorized in 1947, and people started to make attempts to produce this material in the 60s and 70s. The name graphene was first coined in 87. But nobody really succeeded in producing a single sheet of graphene, a single sheet of carbon, until 2004, when Professor Gaiman Novoselov from the University of Manchester first isolated or produced this single sheet of carbon atom. So as you can see, it's a relatively young material. We're only in 2021, so it's about 16, 17 years old. And a few years after that, Andrei and Kostya were awarded the Nobel Prize in Physics, essentially for discovering or producing the world's first two-dimensional material and kickstarting this revolution of materials in two dimensions. Okay, so that's sort of the brief history of where we get graphene and 2D materials from. Now, the structure of graphene and everything that I told you about, the single atoms and stuff like that. This is not theoretical. I mean, we can actually see this with our own eyes. So we've got these things at the University of Manchester and in other places called transmission electron microscopes, which many of you might be familiar with, where you can actually look and see the individual atoms in any material using electrons instead of light for actually viewing these materials. So this is a transmission electron microscopy image of graphene, and you can see each white dot, that's a carbon atom. And you can see how these carbon atoms are arranged in hexagons. It's like a chicken wire type structure. And you can also see right in the middle here, this big black area, the small black area, where there is one carbon atom missing. So the reason I put this picture instead of the picture of like a perfect sheet of graphene is just to emphasize that these kind of defects, they occur in nature, they occur in everything. So even graphene is not like perfectly defect free. You will always find these kinds and all other kinds of defects in a graphene structure when you look at it under the microscope. So that's what graphene looks like. You can see the individual carbon atoms, they're arranged and how they're arranged. That's a single sheet of carbon. So now that we have this material, so why are we so excited about this? It's a single sheet of carbon atom, which makes it the thinnest material in the world, but that could just be a curiosity. So, but actually it's much, much more than that. What we have here is the world's strongest material. So despite being one atom thick, graphene is actually the world's strongest material in terms of its strength. So what strength, the force you have to apply to break it by pulling at this single sheet of carbon atom. It's actually almost entirely transparent, which you might expect because it's a single sheet of carbon atoms. However, even a single sheet of carbon atoms, despite being just one atom thick, it actually absorbs quite a lot of light for that one sheet of carbon atom. So depending on which way you look at it, you could think of it as the darkest material in the world, because for a given thickness, it is actually absorbing the most light of any material in the world. Or you can think of it as very transparent, because it's just one atom thick, most of the light goes through it. So it depends on how you look at it, which is quite interesting. It's also very light in terms of the weight per unit area. It also has the highest surface to volume ratio. Essentially, every atom in this material is exposed to the environment, actually exposed to the environment twice, because once at the top and once at the bottom. But also it's the best conductor of electricity and heat. It's better conductor of electricity and heat than copper or gold or any of these metals. It has the fastest moving electrons of any material in the world. It's also very stretchable and flexible. You can bend it and twist it without breaking it. It's completely impermeable, which means that if you have a perfect sheet of graphene without these defects in it, not even like an atom of helium can actually go through that sheet of graphene. So it's impermeable, completely impermeable. It's chemically quite stable, and so on. So it's actually it's not just this list of properties that makes it so amazing, because you can think of maybe one material somewhere else which has a better conductivity, or a stronger material, or a more transparent material. But graphene is special because it's all of these properties that are combined into one material. And actually, and you might also notice that I've got these 3 dots right at the bottom. What that is intended to signify is that the properties list is actually still growing. As we do more research, more fundamental research into graphene at the university, we're actually discovering more amazing properties of graphene. So this is not by any means a complete list of properties. So I'll spend a little bit of time telling you about how to make graphene, because I think that's quite interesting, actually. I told you, if you remember, that in 2004, graphene was made for the first time by Andrei Geim and Kostya Novoselov at Manchester University. But what is really elegant and cool about this is the way that they actually made the graphene, which is a very simple technique. So you can think of this as the technical term for this is micromechanical exfoliation or micromechanical cleavage. But what it actually involves is you take graphite, which I explained before is many layers of carbon atom. You stick a sellotape or a sticky tape to the top sheet of the graphite, and you peel a few layers off. So then you're left with a sheet of sticky tape with few layers of graphene on it. And then you stick another piece of tape to it and you peel it again, and you make these few layers even thinner. So you keep doing this, and ultimately you end up with a few pieces of single layer of carbon. So if you then put this down on a surface like a piece of silicon wafer or something like that, you will get, and look at it in the optical microscope, you get something like this, a picture like this, when you look at this graphite in the optical microscope. All these yellow bits you see here, that's thick sheets of graphite, more than 10 layers of graphene. But then you start seeing some blue pieces here. That's where you start getting really thin sheets, few layers. As it gets more purple, it gets thinner and thinner. Now, if you zoom in to a higher magnification, then you can pick out some nice regions like that on the right-hand side, where you can see different shades of purple. The purple in the background, that's the substrate, that's the silicon wafer. And then this very light shade of purple, darker purple that you see, that's one layer of carbon atoms. So it's really actually cool because despite being a single sheet of carbon atoms, a single atomic layer, so the super thin material, you can actually still see it in just an optical microscope. You don't need an electron microscope to see graphene. And the slightly darker region, that's 2 layers of graphene. And as it gets darker and darker, you go 3, 4, 5 layers. So just by looking at the color, you can actually count the number of layers of graphene that you have. So the analogy for this, 17 years ago when graphene was first made, and the researchers in the lab, they saw a picture like this under the microscope, and then they have to basically go hunting for the little piece of graphene like this one here. So it's kind of like, where's Wally? You have this picture, and then you need to go looking for where is the graphene? Where can I find it? Because the graphene pieces back in 15, 17 years ago were really, really, really small. So that piece of graphene there is probably 100 times smaller than the thickness of human hair. So it's really small, but you can still see it in the optical microscope at a high magnification. One of the things that is nice, remember I told you about before that, it's just a sticky tape process. So actually anybody can make graphene if you have a good enough microscope and lots of patience. So you can use sticky tape and you can make your own graphene and look at it under the microscope. So that's a picture from some outreach that we do every year, where we take a microscope and some sellotape and graphite, and we go to science festivals and things like that, and we have people come to the stand to make your own graphene. Unfortunately, for the last year or so, we haven't been able to do that. But hopefully, fingers crossed, in some time, in a few months maybe, things will get better, and then we'll be back to doing hands-on graphene activities. So keep your eyes open. Manchester Science Festival, for example, we will be there, and you can come and make your own graphene as well. But that way of making graphene with this sticky tape and things like that, it's not exactly what you would call scalable. You can't make useful quantities of graphene by that method. So you have to develop, or we have developed, ways of making large amounts of graphene, one of which is known as chemical vapor deposition, where you can basically grow a sheet of graphene on top of metals, a single sheet of graphene. And this process can be scaled up, and you can actually, nowadays, you can grow the graphene in what is known as a roll-to-roll process. So you can actually make large continuous sheets of graphene of any arbitrary size that you want. You can also take graphite, and instead of going at it with this sellotape, you can actually use a process known as solvent exfoliation, where you break apart the pieces of graphite into graphene in water or something like that, using ultrasonic energy or other kinds of energies, or using chemical processes. And you can get like an ink, like a bottle of little pieces of graphene floating around in the liquid. So these are large scale production techniques of graphene. There are also other ones. You can grow the graphene instead of on metal, on silicon carbide. You can assemble it using molecular assembly on surfaces. So there are different ways of making graphene. Each way of making graphene is going to give you a different property of graphene. So some might be small particles, some are big particles, some have less defects, some have more defects, some are, and so on and so forth. So depending on what the application is, what kind of graphene you need to use, you can make the graphene using a different method. And also, depending on the method of making the graphene, the price of the graphene is also going to be different, which also correlates with quality. So it's very important to know and understand the correlation between the properties of graphene and the price of graphene and the application. Before I go into these applications of graphene, just a nice little story, actually. Remember I showed you before this picture of silicon, where you can see these single sheets of graphene. There's a bit of serendipity involved in the discovery of graphene as well, because you can only see these nice sheets of graphene if you put the graphene down on a very specific kind of surface. If you change, for example, the kind of graphene and sorry, not kind of graphene, the type of the substrate, then you can't see it. And the serendipity involved in the discovery of graphene is that on that particular day, or during that experiment in Andre and Kostya's lab, they accidentally happened to use the correct thickness of material to see the graphene. Otherwise, they might have missed it. So there's always a bit of luck involved in graphene, in science in general as well. So for the next 10 minutes, 15 minutes, I'll talk a little bit about the applications of graphene. So, we discovered, the Andre and Kostya discovered graphene about 17 years ago, but very quickly, people realized the potential for graphene in various applications to enable new technologies. So, for example, one of the first things that really got people excited about the potential applications of graphene, remember I told you before that graphene was transparent. It's a good conductor of electricity. It's flexible. So people immediately thought, okay, if it's a good conductor of electricity and transparent, that those two are actually very difficult properties to have at the same time. If you just look around and think about it, good electrical conductors are almost never transparent, like gold and copper, because the property that generally makes materials good conductors, which is having lots and lots of electrons, is also the same property that makes materials absorb a lot of light. So if you have lots of electrons, materials will absorb lots of light. However, graphene is very different. It's not a good conductor because it has lots of electrons. It's a good conductor because even though it doesn't have so many electrons, the electrons move very fast. So for that reason, graphene is one of the very few materials that is actually both a good conductor of electricity and transparent. And you need that for things like coatings on touchscreens, for display applications. At the moment, almost all displays use a coating of something known as indium tin oxide, it's an okay conductor. It's transparent, but one thing that it is not is it's not bendable. So if you want to make bendable flexible, we've got bendy phones now for since about a year or two ago. We've started to have flexible displays. So one of the materials that has the real potential for the future of fully flexible displays is graphene. And there are some companies, big names like LG and Samsung are looking into graphene as one of the potential future materials for use in bendable and flexible display technology. Another application of graphene is in composites. So by composites, what I mean, as the name suggests, a composite is a mixture of two kinds of materials. So in this case, for example, you can have a polymer or a plastic, rubber, materials like that, which generally tend to be quite soft and brittle, not very strong, not very robust. And you can add graphene into them, and graphene will share some of its properties with this polymer, so with the plastic, with the rubber, which means you can make your polymer to be stronger, more electrically conductive, more heat conductive, a better barrier. And all of these have potentially various applications. Like, for example, if you take a food packaging, for example, and you use plastic now, if you infuse the plastic with graphene, you make the barrier properties of this film better, which means your food will last longer. You can use it also in other things like rubber to make the rubber more durable and more long-lasting. On the last slide, I'll explain, or I'll give you an example of how that's being done in the real world. So composites can also, if you make your composite like a plastic or something like that stronger, you can also, we make a lot of things with plastic, even, race cars and things like that, where weight is very important. You can make that composite lightweight, and then you can actually have weight savings and fuel savings and things like that. Lots of applications for composites. Another very exciting application of graphene is in filtration. So I'll come to graphene derivatives and modifications of graphene later, but one variation or one modification of graphene has a unique property, which is that it can allow water molecules to pass through very easily, but it does not allow other things like dissolved salts, or when you have water and alcohol mixtures together, it only lets the water through and not the other stuff. So it's a filtration membrane, but it's actually a nano or ultrafiltration membrane. So you can separate alcohol and water, which is very important for biofuel production. You can separate salt and water, which is very important for desalination. But there are other kinds of graphene materials which are completely impermeable to water, modifications of graphene. So you can use those kinds of materials for things like corrosion protection. So whether you use graphene as a barrier or as a filter membrane, there's a lot of applications in these films of graphene as well. The things that I've told you about before, composites, coatings, these are much closer to a real tangible application that you might actually be able to go out and buy. But there are also some things which are much farther out in the future, like medical applications of graphene. There's lots of research that has gone into things like using graphene inside the body for delivering drugs or for detecting diseases and things like that. But this is all very, very experimental in the lab kind of stuff, because to develop something like this, a nano biotechnology from the lab to the real world, takes a very, very, very long time. But there's a lot of interest, a lot of potential, but we might get to that at some point in the future, maybe 20 years from now. You might actually have applications of graphene inside the body. But there are applications of graphene in medical settings outside the body, which is a lot closer. For example, sensors or screening, like for detecting, for blood tests and saliva tests and things like that. You can actually build sensors or assay kits from graphene, and we're working on that as well. So you might have tests for diseases and things like that made of a graphene sensor. That's something which is much closer to a real application. And also other kinds of sensors for detecting gases and chemicals and so on and so forth. This is taking advantage of what I told you before, which is this high surface to volume ratio, good electrical conductivity, and things like that. You can also build other types of sensors with graphene. You can build what I call physical sensors with graphene as well. With things like pressure sensors, temperature sensors, touch sensors, force sensors, strain sensors, and all that sort of stuff. So again, this is another area of research where I'm personally quite active in. We have developed some graphene-based pressure sensors and touch sensors, which is quite getting closer and closer to sort of a product or application. So, in the next few years, you might start seeing graphene sensors for pressure and touch coming out from the university in real products. Another very exciting area for graphene is in optoelectronics. Well, actually, not so much graphene, but other two-dimensional materials. And again, I'll tell you about other two-dimensional materials in a bit, but there are other materials like graphene, which are single atomic layers, which can be used for making solar cells. So when the light falls on them, they convert that light into electricity. And also photodetectors. By photodetectors, I mean like the sensor that you have in your camera. So again, it's the same principle. Light falls on the graphene or light falls on these two-dimensional materials, and it converts the light into electrons, and you can detect that as a current, and you can use that for detecting light. So again, this is another area where products are starting to be developed. There are prototypes and concept devices for things like night vision and for automotive applications and various things like that. Broadband photodetectors made out of two-dimensional materials, which in the next few years will hit the market. So we're getting very close to applications in these areas. Another area where there is, again, potential for applications very soon, because there's, again, quite a lot of products in prototype stage, is energy storage. So by energy storage, I mean batteries, supercapacitors, ultracapacitors, hybrid battery supercapacitor combinations, and things like that, where the graphene is actually used as the electrode material. Now, this is not so novel in the sense that batteries and supercaps already use graphite as their electrode material. So it's just going from graphite to graphene. But there's a lot of technology involved in doing this. But what it allows you to do is make the battery electrodes much thinner and better conductors, which means that you can pack more charge, more energy into a given amount of volume or a given amount of weight. The energy density is very high, which means that you can get more mileage, for example, if it's an electric car, out of the same weight of the battery. But also, you can make things like very thin, flexible batteries if you want to make a flexible electronic device, like a flexible phone, which is not just flexible in one part, but the whole thing is bendable and flexible. You need flexible batteries for that. And also because the graphene is a very good conductor, you can also have very fast charging batteries, which means that, instead of charging your phone overnight, you might be able to charge it in 10 minutes and so on. So applications of graphene in energy storage is gaining a lot of interest as well. So yeah, those are some examples of various applications of graphene. And it's for this reason, for the discovery of graphene, for studying and understanding its various properties and demonstrating many of these applications for the first time that I talked about today. Andrei Geim and Kostya Novoselov were awarded the Nobel Prize for Physics in 2010 for groundbreaking experiments regarding the two-dimensional material graphene. And they have since then received, obviously, lots of other accolades. They've been knighted. They are fellows of the Royal Society. They've been given keys to the city of Manchester, and so on and so forth. So one of the nice, interesting little tidbits about Andrei Geim, he's actually the only person in the world to have won both the Nobel Prize and the Ig Nobel Prize. The Ig Nobel Prize, for those of you who have heard of it or not heard of it before, is given by Harvard University for essentially funny experiments or interesting or curious experiments that make you laugh. So this was, Andrei Geim was awarded the 2000 Ig Nobel Prize, essentially for what is now essentially a staple of textbook physics, which is known as the flying frog experiment. Basically, what he showed was that if you took a really large magnet and you put any living or biological material in there, frogs, strawberries, whatever, it can float inside the bore of the magnet using a property known as diamagnetic levitation. So nowadays, that's actually, if you can go on YouTube and do flying frog experiment, and you can see this for yourself. But at that time, it was a real curiosity, and even now it's hilarious. So Andrei Geim has that accolade to his name as well. So going on from that, I will just tell you a little bit about other kinds of 2D materials. We've got modifications of graphene. I mentioned before, you've got graphene oxide, which is graphene with oxygen atoms attached to it. Graphane with an A, which is graphene with hydrogen atoms attached to it. You've got fluorographene, which means graphene with fluorine atoms attached to it, which all have very interesting and unique properties. And fluorographene, for example, is something which people can easily relate to, because just like graphene is one layer of graphite, fluorographene is one layer of Teflon. Yeah. So we're all familiar with Teflon, but it's essentially one atomically thin layer of Teflon. And also, I also mentioned this before, there are other materials which have also, since graphene, since 2004, people have started making other materials also in single sheets. So these other materials can have, for example, boron nitride is an insulator. I told you graphene was an electrical conductor. Boron nitride is an insulator. Molybdenum disulfide is a semiconductor, and so on. So each of these materials, which all of these are much, much newer. So, it would be, it doesn't have the whole presentation about these materials because they're quite new. We're still learning about them. But, maybe in 10 years' time, I might be able to give a full talk about molybdenum disulfide in the same way that I'm talking about graphene now. So this is the future of graphene-like materials, where we go next, what the future materials in two-dimensional materials that we are going to be studying and we're going to be playing with and making applications and things like that. But where this gets really, really, really exciting for me and for lots of other people. So here is a list of two-dimensional materials. I told you molybdenum disulfide, boron nitride, graphene. These are all single atomic layer of materials, right? And then what you can actually start to do, where this gets really, really exciting, you can build new materials, where graphite is just layers of graphene, right? Instead of that, you can have one layer of graphene, one layer of boron nitride, one layer of molybdenum disulfide, another layer of graphene. And then you enter this space of genuinely man-made materials, because things like graphite, for example, you can find it in nature, multi-layers of the same material, you can find it in nature. But nowhere in nature will you be able to find one layer of graphene, one layer of molybdenum disulfide, one layer of boron nitride. So this is really genuine man-made materials. One of the very few things that you can say, there is no way anywhere in the universe are you going to find a material like this that has been formed naturally. So this is genuine man-made materials, these heterostructures. And you can actually then start to think of electronics, like your computer chip. Instead of having a thick gold wire and a piece of silicon on top of that, you can actually have electronics where everything is a single atomic layer. So a single layer of atomic layer conductor, a single atomic layer insulator, a single atomic layer semiconductor, and so on. And this is not a pipe dream. I mean, already, for example, last year in the European Graphene Flagship, which is a big consortium of graphene researchers, the first pilot graphene semiconductor line has been commissioned, not commissioned, has been or will be commissioned in a couple of years. That they've started putting it together, where just like in Intel or any of these places, they have these fabrication lines for semiconductor devices. This will be a fabrication line for graphene electronic devices. So we're actually getting there. I mean, this is going to require a lot of investment to build these large fabs, but we're getting there one small step at a time. So this is, again, something which will become reality, but it's going to take time and lots of effort and investment, but we're getting there. The last few things I'll talk about today, why do I have a picture of Glamour magazine? This is from a few years ago, but I found it really interesting because they have this feature about, welcome to your career future. I just thought I'll put this in because, this is the futurist stock. So what could be your future career? Number 4 on the list in Glamour magazine was graphene engineer. Now, I'm not saying you should take career advice from Glamour magazine necessarily, but what I'm trying to convey is that the idea of graphene is now starting to permeate into mainstream pop culture, let's say. It's been mentioned on things like Big Bang Theory and stuff like that. So yeah, people are hearing more and more about graphene and two-dimensional materials, and in 10, 20 years, it might become much more well-known than it is today as more applications and more products start to be used in everyday use. So, but how are we going to get there? It's not easy to get from making things in the lab to actually getting things into industry, getting things into people's hands and going to the shop and buying it. Because in the universities, we generally tend to work on very fundamental scales. There's something known as the technology readiness level. It's a scale that goes from 1 to 9. 1 represents basic research, 9 represents real world products. So academia generally tends to work at what we call low TRL, TRL 1 to 3. And industry works at high TRL, so 7, 8, 9. How do you bridge this gap, or what people refer to as the valley of death? So lots of new ideas, new concepts are developed at universities, but you need to get it through with lots of investment in money and time and scale up from the lab into the marketplace. And this generally doesn't tend to happen very well. And the UK has had lots of examples of where we've developed some very interesting things at universities, but we have not invested or not succeeded in getting things over this valley of death. And that's been done somewhere else. So the people who actually benefit from it, profit from it, the companies are not in the UK, even though the original concept was developed here. So we didn't want that to happen with graphene. So the government has invested quite a lot of money into bridging this gap, this valley of death at the University of Manchester. We've got 2 facilities to allow us to do this. One is the National Graphene Institute, which is still low TRL, but industry focused application and technology development. And then we've got the Graphene Engineering Innovation Center, which is medium TRL. So technologies developed in the lab can be scaled up in these buildings and then taken to application. So we are trying to help companies bridge this gap between university and industry to actually try and get more products into market. The Graphene Engineering Innovation Center, or GEEK as it's affectionately known, is only about 1.5 years old, 2 years old. So it's a very new building. We're hoping that lots in the next few years, lots of new products and applications will come out of the GEEK. So again, I want to invite you all when things get better, when the Manchester Science Festival and other science festivals around the country. If you get a chance to come to one of our stands, please do, and you can help. You can learn about graphene and how to make it and things like that. Penultimate slide, I just want to also acknowledge my research group. We're about 20 people based in the National Graphene Institute, which I mentioned before, and also in the Department of Materials, working on composite materials, sensors, biomedical applications, and lots of different things that we work on. So these are the people who do all the hard work, and then I come to get the chance to come and tell you all about it and have all the fun while they toil away in the lab. So I should acknowledge them and thank them for their hard work. So before we finish, I'm just going to play you a video about a graphene product which is on the shelf today that was developed in my group. We released this product about a year and a half, 2 years ago. You can go out to a high street store or online and you can actually buy this product. I'll play a little video and then I'll tell you a little bit about it after I've played the video, and then we'll stop with that, okay? So let's hope this works. And the video, hang on a minute. Yeah.
Innovate was founded 15 years ago. The brand has grown. At the heart of the business is always innovating in product.
We have been working on graphene composites, particularly graphene elastomer composites like rubber and polyurethane, for a few years now, and we were aware of the significant improvement that graphene can bring to these materials.
We started collaborating with the University of Manchester when I was intrigued about the potential for graphene being included in our products. We initially used the EPSRC IAA fund to prove the concept.
I developed the first graphene rubber compound, which gave significant improvement in grip and durability.
Normally, you have a compromise in rubber. If you need it to provide good grip, it needs to be a soft rubber, which also tends to wear away very quickly. So by adding the graphene to this rubber, we've been able to get a new compound which has both the elasticity required to give superior grip and also the durability required to make it last long.
As soon as we found out that it had the potential to bond with rubber and could be used in the soles of our product to strengthen that rubber and increase the performance properties of the rubber, it really just spiraled from there.
We're now continuing the collaboration through a KTP project, which continues the development of this compound, optimizing it, improving it, and also to incorporate the graphene into other parts of the shoe beyond the outsole.
I'm continuing to support the collaboration with Innovate by sharing my expertise with the new KTP associate and training him on the lab equipment and processes.
The main aim of my role is to essentially transfer the knowledge gained from the National Graphene Institute to Innovate so that they can use the knowledge and the skills across their business. I think the combination of both research and industry exposure has been very positive.
Athletes no longer need to compromise. We've delivered the world's toughest grip, which is 50% stronger, 50% more elastic, 50% harder wearing.
It's very rare that a new material comes to market that can give such significant performance enhancement benefits to a product.
We launched this product on July the 12th, and we had press from around the world at that launch event. The product has been received incredibly well.
Any knowledge generated in the university is best served if it actually results in some impact for society, and this can only realistically be achieved if we have a strong partnership between business, which is going to take the technology from the university and translate it into the real world.
It's about getting the science and academic knowledge that we have in universities across the UK and sharing that and imparting it on business so that British business can go out there and lead the world in innovation.
So yeah, that's a product which you can go now or either on Innovate website, or you can go to Ellis Brigham, for example, on Deansgate and walk into the shop and you can buy a graphene product, which is for gym or running or hiking boots and things like that. They'll actually keep your eyes open. Next week, we'll be making another announcement about some new developments in this project and new products coming out of this as well. So I'll stop at that. And I can see in the chat there are questions coming through. So I'll let me know if you want me to close the presentation maybe, and then I can field some of your questions.
Yeah, so if we close the presentation and then we'll go to questions now. Great, well, wow, where do we start? I'm not normally blown away by things, but that is the magic material right there. And we've got a lot of questions in the chat, just a lot from YouTube and a lot from other social media. So looking at them, they sort of break down into two things, sort of questions about the material itself and then about the uses. So we'll start with those that are about the material. So a question from YouTube is, does 2 dimensions refer to the bonding directions rather than thickness? So they're asking as a non-expert that thinking that even if something is one atom, it still has a dimension.
Okay, so that is a very interesting question. And yes, I did gloss over the whole thickness part of it when I was telling you about 2-dimensional materials. Yes, you're absolutely right. It does have a finite thickness. So in that sense, it's not strictly 2-dimensional. However, there are 2 ways you can look at it to explain what or why it's a 2-dimensional material. So the first way is the structural explanation, where, remember I told you that the carbon atoms are arranged in a sheet, in a plane, right, in this chicken wire or hexagonal structure. Now, if you add more carbon atoms in that plane and make the sheet bigger and bigger, it still remains graphene. But if you start adding atoms above and below, then it becomes something else. So you can only make this sheet bigger in 2 dimensions and not in the 3rd dimension, while at the same time preserving its properties. So from a structural explanation, that's why we call it a 2-dimensional material. There's also the electronic explanation for why it's a 2D material, which is that if you imagine, well, you have to do a bit of role playing here. You have to imagine that you are an electron and you're living in this sheet of graphene. An electron in the sheet of graphene is only able to move in 2 dimensions. So it can move, in the plane of the graphene, but it cannot move out of the plane of the graphene. So the electron in the graphene is not aware of the thickness of the graphene. It's only aware of the 2 dimensions. It's like, we're living in a 3D world, but there might be a 4th dimension. We just cannot feel it. We cannot travel in that 4th dimension. So as far as we are concerned, we live in a 3-dimensional universe. So the electron in the graphene is living in a 2-dimensional universe. And the properties of graphene, like its strength and electrical conductivity and thermal conductivity, they're actually linked to what the electron is seeing, not what you and I are seeing. So from the electron's perspective, it's a 2-dimensional material. So that's the more involved scientific explanation for why we call it a 2D material.
Okay, thank you. And another one from YouTube, just relating to the 2D materials aspect, is do you think that van der Waals vision can be implemented, limiting the final price of the devices and having a good quality for each of the 2D materials piled up?
Sorry, can you repeat that, Georgia? You're breaking up.
Sorry. Yeah. So do you think that van der Waals vision can be implemented, so limiting the final price of the devices and having a good quality? Okay.
Georgia, I'm having really a difficult time understanding what you're saying. You're breaking up a lot. Okay. You said van der Waals something, but van der Waals what?
His vision for limiting the final price of devices.
I'm not quite sure what is being, sorry, I don't quite know what the question is. I'm not able to understand what is being referred to there. Okay, maybe you can put it into the chat or something and I'll come back to it later.
Sorry about this. It's always bound to happen, isn't it, the first time you try things. So moving on to another question, I'll speak slowly, so hopefully it'll it'll catch up with me. So the conductibility of graphene is impressive. Is there an upper limit on the voltage and amp of when it's passing electricity? Doesn't it change its form in any way?
So, I mean, like any material, if you apply too much voltage or pass too much current through it, it's going to break down. It's going to melt because of intrinsic Joule heating. So if you put too much power through the graphene, it will be destroyed. But the amount of current per cross section, so the current density of graphene that you can put through the graphene is impressively high. But that doesn't mean that you can put absolute amounts of current, a large amount of current through the graphene. You have to think of it as scaled down to the single atomic layer. But then again, you're not going to be using a single sheet of graphene to replace a thick copper wire either. You're going to use it in applications where the amount of current that goes through the graphene or the voltage that you apply are going to be quite small, like in a transistor in a computer chip or something like that. You're not going to use the graphene to replace the copper wiring in your house. So yeah, you can't put a huge absolute amount of current through it, but the current density for that thickness of graphene is higher than any other material.
Great, thanks very much for that. We're just going to take over because of technical issues. So the next question is, what pricing levels have to be achieved for graphene before large-scale commercial adoption is achieved?
Like I said in my presentation, we already have commercial graphene products like the shoe, which, for example, price is important. So, the reason why the first graphene shoe is a high-performance sports shoe, which costs over £100, and not a pair of flip-flops that you get for £10, is because of the cost of graphene. Certain products which are more niche can tolerate the price of graphene at today's prices. But as the production is ramped up, as more and more products come online, the economies of scale kick in, the price of graphene starts to come down, and more widespread application can occur. So this is just the start of the graphene application. Price is one of the limiting factors. And we hope that, as more applications come online, it's a bit of a chicken and egg situation, which is one of the reasons why the Graphene Engineering Center is been built. We want to get more products out there, which will incentivize the producers to make more graphene, which will in turn bring the price down, which will in turn allow more companies to make graphene products. So yeah, we hope for that to happen over the course of the next few years.
Okay, and here's one you might not be exactly able to tell us, but you might be able to give us a hint. Are you working with any large-scale manufacturers at the moment? What's coming up in the future that you could maybe give us a hint about?
I can't say specifically about individual products, but we've got dozens of companies working with us at the Graphene Engineering Center. Many of them, including graphene producers, actually have labs based in the Graphene Engineering Center. We're working closely. There are companies that I work with in my lab as well. So yes, we do expect new applications, new products to come out in the next 5-10 years time, maybe some even in the next 1 or 2 years. But for various commercial reasons, I can't really say specifically we're going to get this or that yet until the companies are ready to tell you.
Yeah, I thought that might be the case. I was just hoping. Has graphene yet been used in the fight against COVID in terms of the medical industry? Because you talked about that earlier.
Yeah, I mean, the biomedical applications of graphene, like I said, to get something into the body is going to take a long, long time. So it's not something that you can do right now, unfortunately. There have been, there are things you could do in terms of biosensors and stuff like that, in terms of building a COVID sensor, is something which I'm working on at the moment as well, where we're working on technologies to detect viruses and antibodies and things like that. We've not done it specifically for COVID, because getting your hands on COVID samples is not particularly easy thing to do. You need to have specialist labs and facilities to be able to do that. But in principle, you could, because earlier last year, we published a paper on how you could use graphene as an antibody test for another kind of disease, for a kidney disease, when we are going to look at applications, so sort of scale that up into something real world. And maybe we won't be able to help with the COVID effort, but heaven forbid, if this ever happens again, maybe we'll have something for the next one.
Yeah, that's great. So one of the questions is about the batteries. Obviously, we know very much about some battery manufacturers, especially in electric cars. We're just wondering if it is, if it has actually been used in the Tesla. Is it being used in some of these electric cars so far?
There are prototypes of graphene batteries. It's not been put into a full commercial use yet, because there are various scale-up issues and things like that which are being addressed. It's one of the areas where we expect there to be applications, real-world products in the next few years. But again, getting a new electrode material into something like batteries, there's also a huge amount of quality control and safety considerations and things like that. If you want to put a graphene battery to a car or something like that, the amount of testing that goes into that is phenomenal. So yeah, we were working on it, but nothing in the market just yet.
Okay, that's great. You've also mentioned multiple exciting ways that graphene is being used. What's personally for you is the most exciting way it's being used?
Ooh, that's a difficult one. I think the sensors area is particularly exciting for me. We're working on things like pressure sensors, touch sensors, biomedical sensors, like I mentioned before. Yeah, I mean, that's something which I find very exciting in my group. And with the composites as well. We started with the shoes, but there are lots of other exciting things that products that could use that sort of the strength and the conductivity of graphene. So yeah, those are the two main areas in my group that I focus on.
Okay. Thank you very much for that. So I'm going to try and unpack this question that we tried to ask earlier. It's a little bit of a long one, and I don't fully understand it. So you might help us with this. So it's do you think the Van der Waals version, which I think you talked about, can be implemented in such a way that would limit the final price of the devices, and therefore having a good quality for each 2D material piled up? That's the question. I think it's quite a long question, isn't it?
The problem is I don't understand what the Van der Waals vision is. I've never heard of that phrase before. So if somebody can explain to me what they mean by the Van der Waals vision, I can answer the question.
Maybe if JT is still online, if he could help us with that would be brilliant, because it would be lovely if we could answer it if possible. Okay, so another very technical question on car batteries here. Again, it's about companies you might not be able to tell us. So what companies are focused on the graphene battery supercapacitor, and how much graphene would be required for a typical car battery of 100 to 150 kilowatts? Sorry, kilowatt hours, sorry.
Yeah, energy storage is not my field, so
Okay.
Unfortunately, I'm not able to give you specifics on that.
This is great. We just think you know absolutely everything about graphene. So it's really cool. It's really cool that there's maybe just a couple of things you might not know, but it's brilliant. It's brilliant.
I'm not infallible. I'm not infallible. There's a few things that I don't quite know yet.
I'm just reading down for the last two questions. So another question, your pressure sensors and temperature sensors, again, what range and precision do they have? So I think it's about, how accurate can they actually be?
I would have to look this up. I mean, I don't know off the top of my head.
We're giving you all the hard ones, aren't we?
Okay, let me tell you this. For pressure sensors, for example, we can actually detect the weight of a single atom. So we can actually build pressure sensors which are so sensitive that even if a single gas molecule lands on top of that graphene pressure sensor, we can detect it. So there are ways for us to build super sensitive graphene pressure sensors. Similarly with temperature as well, we can build them in the lab to be super sensitive to even the smallest change in temperature and pressure and force. The real question is, what can I build in what can we actually build that in a real world application? What is the the pressure sensitivity and things like that? That's a much harder question to answer. But we've demonstrated there are papers out there where we've actually shown that there are devices, graphene pressure sensors that can detect a single atom. So that will give you the idea of the capabilities of graphene.
Wow, that is super sensitive. Wow. Okay, so trying to unpack this question. So it's van der Waals, I think.
Van der Waals, yeah, I know what van der Waals forces are, but what do they mean by van der Waals vision?
Between levels. So he's talking about the weak intermolecular forces between layers of graphite then.
Yeah.
So then let's go back to the question, and it's a
Van der Waals vision. I have no idea what that vision is supposed to imply or mean. That's my
okay. Okay, I think we probably should move on that one now. We've tried, but I think there's probably someone in here who's far more intellectual than me trying to ask that question. Okay, so is there any more questions? One of the things would be great to know, and I know I had heard about this when you were doing it. Do you want to just tell us the story about about your structure that you built at Mozzie?
You mean for the science festival a few years ago? Yeah, no, that was a bit of a fun project. This was oh gosh, I even forgot when it was. It was a few years ago, Manchester Science Festival, where we just to explain this concept of the world's two-dimensional material, graphene, single sheet of carbon, attached in this chicken wire structure. So we said, okay, let's have a go at building this plastic model of graphene, which you might have come across in your school physics lab or something like that, where you've got these balls and plastic sticks that you can connect together to make molecular structures. And yeah, I mean, I don't remember exactly how big it was, the one we ended up making, but we had for over a weekend, lots of people coming through. Everybody made like a little section of it, and we put it all together. And this was during the Manchester Science Festival. I think that turned out really, really well. And then, if you go to events in Mozzie now, they do that sometimes as well on a smaller scale. But actually in Mozzie, there I don't know if it's still there or not, but on the top floor, there is still an exhibit which has some graphene samples and things like that there as well. Not really sure if it's still there or not.
Yeah, I mean, I think it was more that, you had a storm the night before, and I remember you kind of talking about, oh, my life, is it going to be there in the morning? But
it was outside, and there was a howling gale that night. It actually held up, so I was pretty impressed with that.
Right. So just a couple more questions before we finish. So one of them, what's the environmental impact of graphene?
That's again a difficult one to answer, because environmental impact is you can talk about it in different ways, pros and cons. If you think about applications in rubbers and composites and things like that, the graphene is going to make your product last longer. So it's obviously going to have a positive environmental impact if you have technologies that can or products that can last longer. You can, if you again, batteries, energy storage, if you can improve the performance of batteries, the energy storage density, the adoption of battery technology in applications which are currently not possible using graphene batteries, again, that's going to have a very positive environmental impact. I'm not going to try and sell graphene as the next green thing. It's not like a super biodegradable material or anything like that. But it all depends on how you put it to use. If you use it cleverly, then you can get positive environmental impact from the use of graphene.
Great, thank you very much. So just another question: what is it being used for now? I've heard lots of things it could do. One of the most exciting is being able to filter salt out of seawater, which has obvious amazing impact. But what is it actually being applied to at the moment, other than obviously Innovate we know about?
Yeah, there are a couple of applications in the automotive sector, again, in very niche products. There's a kit car company called BAC, which makes a weekend racer boy racing car called the BAC Mono, which has graphene composite panels and things like that in there for lightweighting. So it's these kind of fairly niche products which have hit the market in the last 1 or 2 years. A lot of the things that I've talked about today are in prototype stage, so they're all in the pipeline for widespread application. But I mean, the Innovate shoe is probably the one thing which I can point to, which is available around the world. You can go to the shop and buy it. I think it's sold in high street stores in 25 countries or something like that. So that's an example of a real world worldwide application that it's just a starting. I mean, that's where we are today. So in 5 years' time, I might be able to point out to a whole range of other examples. But fingers crossed, we'll get there.
I mean, talking about cars, is it being used in Formula One as yet?
I'm not aware of any F1 companies actually using graphene for lightweighting or anything like that. I think there are some regulations that don't allow it. Not 100% sure. I know for a fact that there are regulations that forbid the use of carbon nanotubes. There might be something like that for graphene as well. So I don't know. I don't think there is. I don't think so.
Brilliant. Okay. And there's just one bit of information. It might be freely available. Is the data on the mechanical the mechanical properties of the Innovate polymer. Are we able to get that? Is there a link that you might be able to, or just tell us to go to the website? Do you know about any of that?
The only information we've released so far is that the graphene is making the strength of the rubber, increasing the strength of the rubber by 50%. And it's also increasing the abrasion resistance, the durability of the rubber by 50%. But we are actually putting a paper together where we will be showing some of the test results from that material as well. So I can't say anything about that now, but we will be submitting something on that, and when it gets published, you'll be able to read that for yourself.
Great. So keep your eyes peeled for that. I'm going to hand back over to Georgia then, as we've come to the end of the questions. But thank you very much.
So I am back, and you should be able to hear me. I'm really sorry about that internet issue. Working from home life, I should have upgraded my internet. But thank you for today. It's been really nice to actually have a conversation and a talk about something that's positive at the moment, considering all the things that we talk about at the moment and the dreaded C word, and actually to talk about something which is so cool, and so many different things are coming out of it that will be so beneficial in 5, 10, 20 years time. So it's been really nice to sort of hear you speak about it, and I think we've all learned something today, and there's been a lot to think about. And yes, so thank you very much for that. It was a really inspiring talk, and we're really glad that you were our first speaker on YouTube, and I'm sure everyone at home has been listening as well. We've got lots of thanks in the comments as well for you, so thank you a lot. And for those of you at home, please remember to like and subscribe. I have to do the YouTube thing. Please like and subscribe to this channel, and you'll be receiving lots more videos from us, and keep in contact with us on social media. Our Twitter handle is @MCRFuturists, and Facebook is Manchester Futurists. So follow us on there as well to keep up to date with everything that we're doing. This video will be on YouTube after the event as well. So if you want to recap any of the things that we've spoken about today, then you're more than welcome to do so. But yeah, thank you to you at home, and thank you to Aravind for such a great talk, and thank you to Caroline for stepping in when everything went wrong. So yeah, thank you everyone, and have a good evening.
Bye.
Bye.